many salt ions can react with H2O to form hydroxide or hydronium. This process is called hydrolysis. So this looks to me like what anion? Chlorite, because you got ClO3 minus 1 memorized as chlorate, right? So that means you know that ClO4 1 minus is perchlorate. Nobody's smiling. But anyway, good stuff to know there. And notice, in the presence of water, we form this weak acid. How do I know this is a weak acid? Well, I know that HClO3 is chlorate, and it's on that list of 7 strong acids. Now, it probably doesn't form much hydroxide, but it forms strong. And it says an anion from a weak acid behaves as a base. Well, it doesn't quite say that on the slide. That's what I'm telling you. Anions from strong acids are neutral. Now, I wish I could zip up all the way to the beginning. Why don't I do it like this? I'm going to do that to my favorite slide of this chapter, and that's this slide here. And so here's the anion of a strong acid, and it says negligible basicity. I say all of these are horrible bases. You put sodium chloride in a glass of water and the pH is going to be 7. You put sodium nitrate in a glass of water and the pH is going to be 7. You put sodium fluoride in the glass of water and the pH is going to be above 7. And then all of these, you put sodium carbonate in a glass of water, it's going to be pH of 10 perhaps. Not super basic, and they're all getting more basic here. And unfortunately, we don't have the chlorite or hypochlorite. Alright, so here's that chloride. Here's HCl. And if you look at this, HCl is a super strong acid. Hydroxide, you can say equilibrium really wants to stay over here. Or if you went into the lab and you titrated hydroxide with HCl, it goes all the way over here. We might even say at the end point, you have a pH of 7. That's a foreshadowing of great things to come. All right, here is hydrogen carbonate. We might call it bicarbonate. And the sodium salt of this is your baking soda, and baking soda is great to have around the lab because we neutralize bases and acids with it. Anions with ionizable protons are amphoteric. So that concept that we just looked at on that big slide that had acids and bases and their conjugate acids and bases from high to low, we can apply these guidelines. Salts derived from a strong acid and a strong base are neutral. So your sodium hydroxide reacted with your hydrochloric acid produces NaCl plus water. This is going to have neutral. Salts derived from a strong base and a weak acid are basic. So the acid here would have been hypochlorous acid, HClO. This looks like the acetate ion, so this would be reacting vinegar or acetic acid with barium hydroxide would give you this salt. So we've identified the weak acid, HClO, hypochlorous acid, and HC2H2O2 acetic acid. Alright, salts derived from a weak base and a strong acid are acidic. So this would be ammonia reacting with HCl. So this was one of the first ones we looked at. Well, the ammonia. So here is the ammonium cation. And if I put something like ammonium nitrate in water, I don't know why I chose to use this example. So salts derived from a weak base and a strong acid. We can bottle this up. You've used it in lab. It's a solid. And if I put that in water, I'm going to get the hydronium ion. So there's the acidic part. Let's go back to this thing here. Salts derived from both a weak acid and a weak base can be either acidic or basic. So here's ammonium cyanide. So to realize what's going on with that, we need to look at the Ka of ammonium and the Kb of cyanide. And if the Ka is bigger, it's going to form an acidic solution. If Kb is bigger, it forms a basic solution. We want to compare and contrast sodium chloride and sodium fluoride. If we were to make aqueous solutions of these, this thing's going to have a pH real close to 7. Why do we know that? Because it's the salt from a strong acid and a strong base. This one over here, if I put this in solution, I'm going to have a pH that's greater than 7. And I want to imagine, well, here's HF, sodium hydroxide. So notice it takes the same form as this reaction here. Acid, base, you get a salt, and you get water. So this salt has some base property, and that's because it's the product of a weak acid and strong base.
So basically, if you have a strong acid and a strong base, they will neutralize, in quotation marks, each other.
Right. The salt will not have an acid-base property.
And then for
but anytime you throw weak in there, the salt has either an acid or a base property,
depending on which is.
Right. So these are weak. Base. These are a weak acid. So this is a weak base. And then if I have ammonia and HCl, I get the ammonium. All right, so this thing is a weak acid. So this salt, ammonium chloride, behaves as a weak acid. I wanted to refer back to this and segue into our next part of this chapter, chemical structure and acid-base behavior. So all of these molecules have a hydrogen. Granted, only water and HF have them written on the left. But we could look at all of these protons and ask whether they're acidic. And it might have to do with this atom here. As it becomes more electronegative, it's easier for the hydrogen to come off. So fluorine is more electronegative than oxygen, and it's easier for the hydrogen to come off. It says here, the more polar the hydrogen X bond, where X is one of these atoms, the weaker the hydrogen heteroatom bond becomes, and the more acidic the compound. So acidity increases from left to right across the low, due mainly to an increase in the electronegativity of the atom, carbon, nitrogen, oxygen, fluorine. So this is to compare what we might call a binary acid. Now going down a column, the acid also gets stronger. Why is that? It says acidity increases going down a group, mainly due to an increase in size, and the hydrogen ion is farther away from the negative charge. That's the general chemistry explanation. We could go a lot deeper and be a lot more eloquent. I'll refrain from picking on organic students. But as we go down, this ion, like bromide, yeah, it's larger, and so the hydrogen ion is farther away, but we might say the bromide is more stable than the chloride, and the chloride is more stable than the fluoride, because we say the charge is what? She's not looking at me. The charge is delocalized. All right, so that's how we explain the binary acids, and we can see H2S is a stronger acid than water. And then when we get to H2SE, look at that, that's increased by a factor of 4 orders of magnitude. 10 to the 4th, 10 to the 8th. I would say this is 10 to the 14th. Where did that 10 to the 14th come from? Yeah, KW. All right, here's where you're going to learn a lot. Oxyacids. What is an oxyacid? Made from one of these oxypolyatomic ions. Oxygen's the most abundant element on the earth here, and we see it in a lot of different compounds and a lot of polyatomic ions like carbonate, sulfate, sulfite, nitrite, chlorate, perchlorate, chloride, hypochlorite. It's all over the place. So this is kind of a funny way to write it, but it's saying Y is any element on the periodic table, and here's an OH, and this H here is the part that's going to donate the hydrogen ion. And it says here, as we make this element Y more electronegative, that can help delocalize this negative charge, or the more electronegative it is, the more stable and happy it is if it has this negative charge. So here it can donate this proton to water. There's the hydronium ion. So here we see chlorine, bromine, iodine. They're all in one group, and so you can remember back to the electronegativity trend that says that electronegativity increases going from the bottom of the periodic table to the top, and we can see that here. Here's the Pauling value of electronegativity for chlorine, 3. For bromine, it's 2.8, and it's going on down. Here's hydrogen, so here's water, and look, oh, there's Kw, my favorite, 1 times 10 to the negative 14th. And so as we increase the electronegativity here, we increase the acid strength. So there's one concept. So now you can tell me whether hypochlorous or hypobromous, which one's stronger. And then the tricky part is if I say you have potassium hypochlorous and potassium hypobromous, which one's going to be the stronger base? And you're going to have to rationalize that. But before we go there, this goes back to the beginning with our 7 strong acids. The day I told you that you had 7, I only had 6 because I failed to double up on the oxy acids of chlorine. With chlorate and perchlorate, put these in water, they become chloric and perchloric. Remember, the 8 becomes ic and the ite becomes us. A little nomenclature review there. So it says here, for a series of oxyacids, acidity increases with the number of oxygens. So when this hydrogen comes off, the negative charge has to be distributed here, and when you pack on more oxygens, which is electronegative, it stabilizes that negative charge more and more. We could say it delocalizes it. So here now I got 4 oxygens on here. Here's a hydrogen bonded to one of those. This is the business end of the acid. This proton comes off. You have an anion that's very stable. And here it's even more stable. So I can ask the question that's probably on your take-home quiz. Which solution will have the highest pH? We want to interpret that and say strongest base.
Isn't it going to NaCl because it doesn't have the more oxidity?
Well, we just learned that this is the salt from a strong acid and strong base, so probably not. Do we have any strong acids up here? Notice these are the conjugate acids of these bases. This here is a strong acid. Perchloric acid, this one's strong. So this one here is a weak acid. So here is the sodium salt of a weak acid. We could imagine, we want to relate it to that PowerPoint slide. When a weak acid is reacted with a strong base, it gives a salt which has some base property. So which solution will have the highest pH? This one here. So how did I figure that out? First thing you want to do is, the next question might say which has the lowest pH. Then it becomes really confusing because it's like a double negative thing. Which is the weakest out of the weakest? Strongest base. It's a weak base, of course, but these are our worthless bases because they come from strong acids. That's the key. That first PowerPoint table we looked at. This one's here is key. All right, everybody's packing up.